welcome to lecture number 17 of VLSI Design KEC 072. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. So, let us continue our analysis of CMOS sequential circuit design. Today, we want to discuss the design of dynamic sequential CMOS circuits. Okay. Before we proceed further and actually discuss our dynamic CMOS sequential circuit, let us take a look back to the static CMOS version of the sequential circuits. Okay. When we ended our last lecture, we had concluded on a positive edge triggered D type flip flop. The circuit which is being shown on your screen right now is the counterpart of it. It is a negative edge triggered D type flip flop. Again, it is a static sequential circuit and based on transmission gates. Okay. So, if we try to analyze the working of this circuit, see it has one transmission gate here, another transmission gate here, 1 and 1. So, this is based on our previously discussed master slave configuration. So, if I draw a line here, on the left we are looking at the master side and on the right we are looking at the slave side. The benefit of this configuration is that it provides edge triggering for register storage, plus the signals are isolated from each stage. So, the signal in the slave stage is isolated from the master stage and vice versa. Okay. So, suppose when clock is at logic high. Okay. So, if clock is 1, clock bar becomes 0, here also clock bar becomes 0, clock here is 1 and here it is 0. Okay. So, clock is 1 here, 0 here, 1 here and 0 here. Okay. So, this transmission gate it is on. So, whatever is present at D is transmitted to this point. Okay. This transmission gate right now, this is off. Okay. So, this does not allow D to pass through, but because of this inverter we get D bar here and another inverter we get D here. So, D reaches at this stage when clock is at logic 1. Further going forward, the transmission gate here, this is off. Okay, because clock bar here is 0 and clock is 1. So, this is off. Okay. So, this does not allow D to pass through. Right now, the master side of this flip flop is in evaluation or the transparent mode, okay, and the slave side is in hold mode. So, whatever output was present in the previous cycle, that is being held right now at the output. Okay. So, suppose now the clock triggers to the opposite side, okay, and clock becomes 0. In that case, clock bar goes 1. Okay. Now, this transmission gate which was on before, this becomes off. Okay. So, if there is any change in input now, that does not propagate through, right, but we have already sampled the input here in the previous cycle. The transmission gate below, this turns on, okay, this one turns on, right, and this one here, if you see, this is now off. Okay. This one is off. So, at this stage, whatever we had sampled in the previous cycle, if D was present here, because this transmission gate is on now, D is moved forward. Okay. So, D propagates forward, it gets inverted here, you get D bar here and further gets inverted and D reaches the output. Okay. So, now you see in the negative edge triggering. So, when we separate the master and slave stages, we see that the master side is on the opposite side of the clock. Okay. So, it triggers, it evaluates on the opposite side of the clock, right, and since on the negative edge triggering, output which was sampled in the previous cycle is reaching the output. So, this is a negative edge triggered flip flop. This is a purely static version of a sequential CMOS circuit. If you look at the entire circuit, all this circuitry is required only for storing 1 bit of data. Okay. So, the major drawback of this type of a circuit is the amount of circuitry, silicon area or the number of transistors which are required here. Okay. And if the number of transistor is higher, a transistor which is a capacitive device, okay, is going to have some amount of delays associated with it. So, number of transistor increases, in that case the amount of delay and power consumption also increases. So, this is the discussion of a static sequential CMOS circuit, and we have seen a major drawback that the typical state logic gate generates its output, okay, corresponding to the applied input voltage after certain delay, and it preserves the output level as long as the power supply is on. It requires a large number of transistors. So, there is more power consumption and more delays associated with it. As the complexity increases, as the circuit density increases, you want delays to be controlled, you want power consumption to be controlled. In this case, area is a major objective for high density large complex circuits. So, in this case we move towards what is known as the dynamic logic circuit, which offers several advantages. Okay. So, dynamic logic gates depend upon temporary or transient storage of charge, okay, in parasitic node capacitances. Now, these capacitances, the source of these capacitances can be the leakage capacitances between the junction between drain and substrate, or the capacitances which produces sub threshold leakage current. All the parasitic nodes, parasitic capacitances, they are used for temporary storage of charge. Okay. So, instead of obtaining or drawing or designing large number of large area latching based circuits, we are using capacitive storage of charge. Okay. Now, capacitor holds its charge, but it does not hold indefinitely. Okay. It slowly discharges also. So, charge leakage is a problem here. So, constant refreshing of internal capacitive nodes is also needed, and this can be controlled by regular clock pulses. Dynamic sequential circuits require less silicon area, they consume less power as compared to static circuits. Okay. So, the problem associated with static version of circuits is the area, number of transistors, that is to a great extent solved by dynamic sequential CMOS circuit, where the storage of charge is done via a capacitor, okay, and that storage is temporary, and to avoid leakage or to avoid the effect of leakage, we use constant refreshing. Okay. But even though an extra circuitry is needed for constant refreshing or storage across the capacitor, but the area advantages offered by dynamic circuit is still very large. Okay. So, let us see one version of a dynamic sequential circuit. Consider a typical D-latch circuit, which is known as a dynamic D-latch circuit. So, if you see the schematic, you have a D input triggered by a clock and one output, okay, a simple latch circuit. What we use is a pass transistor here, which is NMOS. Okay. So, N type pass transistor is used here. The input is applied at the input of this transistor, the clock is applied at the gate. Okay. So, the gate of this NMOS is controlled by the clock. Now, when the clock goes high, in that case this switch turns on. Remember here that an NMOSFET allows signals to pass through when a positive voltage is applied at the gate, but that positive voltage has to exceed the threshold value of that transistor. So, some voltage drop which is equal to the threshold voltage, which is few hundreds of millivolts. So, suppose if you apply a 5 volt signal here, say about 0.7, 0.8 volt might drop across the transistor also, okay, and the remaining goes through. So, as long as you are above the VIH input high level, input high reference level for logic 1, we are okay with this type of circuit. Okay. So, whenever clock goes high, whenever it goes from 0 to 1, positive edge triggering, D is sampled at this node Vx. Okay. Cx is your parasitic capacitance across which charge is being stored now. It is inverted here. So, you get D bar, okay, and inverted again, and D reaches at the output. This happens when clock goes high, and when the clock goes low, it goes from 1 to 0. In that case, if clock goes from 1 to 0, at that time this becomes a open switch. So, whatever changes happen at D now, they do not reach Vx, but Vx is already holding whatever was present at D. Okay. Initially it was sampled. So, that is being held here. As long as the discharging time of the capacitor, okay, is sufficient enough to counter the clock period, this D will not leak away. Okay. So, this D will remain here, it will be considered as logic 1 if 1 was transmitted initially. Okay. In that case, this D will remain here, this D bar and followed by D will also remain here. Okay. So, now you see this is how you use a capacitor here to store the charge, okay, and that charge was sampled in the previous cycle and is being transmitted. Compare this to the initial static CMOS circuits which we had. The amount of circuitry has considerably reduced now. Okay. So, the area required to implement this type of a circuit, a dynamic sequential circuit, is way less, okay, way smaller as compared to a static circuit. In addition to a pass transistor, you can also use transmission gates. We know what is a transmission gate. You have one PMOS and one NMOS driven by complementary clocks. So, a signal always gets transmitted, whether it is logic 1 or logic 0, it is transmitted with equal strength. An NMOS passes a strong 0, a PMOS passes a strong 1. So, best of both complementary circuits is taken into account, right. So, if I have a transmission gate here T 1 followed by an inverter here I 1, another transmission gate T 2 and another inverter here say I 3. Okay. Suppose when clock is 0, so clock bar becomes 1, whatever is present at D gets sampled at node 1, that gets inverted here D bar and it is stored here. Okay. On the opposite side, when clock goes 1, so clock bar will go to 0. Okay. In this case, this transmission gate will be off, but if this is 0 and this is 1, this transmission gate T 2 turns on now, and whatever was present here D bar gets sampled here across capacitor C 2. After this inverter, it reaches the output. Okay. So, this is how, see again this is also based on your master slave concept only. Okay. So, this is your master side on the left and the slave side on the right. So, when clock is 0 or when clock is basically falling from 1 to 0, the input D input gets sampled across node 1 capacitor C 1. On the opposite side of the clock, rising edge of the clock, T 1 goes off and T 2 turns on, okay, and whatever was sampled in initially in the previous cycle is now transferred to the output. So, see again that edge triggering is taking place here also, but this is taking place via transmission gate. Okay. How it is different from the pass transistor version? If we go back to the previous slide, you see this pass transistor here, this is N type MOSFET. If I connect lot of pass transistors in cascade, every pass transistor will have a small voltage drop across it, which is equal to its threshold voltage. So, while by the time we reach the final output in a cascaded version, a lot of voltage drop would have taken place across different transistors, and it is possible that at some particular capacitive node, the output basically falls below the signal across the capacitor falls below VIH, input high level reference. Okay. In that case, we will sample a wrong input, okay, and that will in the next cycle be propagated to the output, right. So, that is a disadvantage that is to some extent sorted out in the transmission gate version, okay, because you have both PMOS and NMOS. So, either one of them is going to transfer the signal with good strength, right. In that case, that voltage drop problem is not there, but there is another issue associated with the transmission gate dynamic circuits, which is known as the clock overlap. Okay. The source of this issue is clock overlap, and what it results in a race condition. Okay. Now, in the transmission gate dynamic logic, we are using complementary clocks. This is still a dual phase system. You have clock here and you have clock bar, you have clock bar here, you have clock here. Okay. So, to produce clock bar, what you would do normally is, if this is your clock signal, you would pass it through an inverter and you will obtain the clock bar. Okay. Now, inverter is nothing but a circuit made up of transistors only, transistor have delays. So, this inverter will also have certain propagation delay. So, suppose your clock is high and then it is going 0, this is clock signal. Okay. Clock bar would be 0 initially, and after some propagation delay now it will go to 1, this is clock bar. Okay. So, see there is a small time period here where both clock and clock bar are actually equal to 0, when they should be complementary to each other. This is known as 0-0 overlap. The opposite is also true. If the clock goes from 0 to 1, clock bar does not go to 0 immediately. There will be a small period of time when clock and clock bar both will be equal to 1, that is known as 1-1 overlap. Okay. So, what will happen in this case, if we go back to the circuit, if clock here is 0 and clock bar is also 0, if clock bar is 0 here and clock is 0 here, you will have a path from this NMOS to this PMOS here. But what we actually want at this stage is that the slave stage should be in evaluation mode, but master stage should be in hold mode. But it is possible that while the output is being evaluated, some new input might get sampled, right, and that might change your output, which is an erroneous operation, right. The opposite also true, when clock is 1 and clock bar is 1, it is possible that another path might exist from here to here. Either way, some new data will be sampled and might make its way towards the output. This is not what we want. Our main advantage of using master slave configuration was that both the stages should be independent of each other. When one is evaluating, another should be in hold. When the slave stage is evaluating, master stage should be in hold mode. Okay. So, in this case there is a race happening. Okay. Because of this race, certain constraints are necessary. If these constraints are satisfied, you can counter this overlap condition. So, the time for which the clock and clock bar at 0-0, okay, whenever there is 0-0 overlap, that time period should be less than the propagation delay of first transmission gate plus the propagation delay of first inverter and the propagation delay of the second transmission gate. If I add these 3 propagation delay and the sum is higher than the 0-0 overlap, then this problem of race will be avoided. Same for the 1-1 overlap, it should be less than the hold time. Okay. If you remember, hold time was the time for which the signal input should be valid when the clock has triggered. Okay. The input should be held for that time. So, if these constraints are satisfied, the problem of overlap can be countered. Okay. But that is something which is a major design constraint, right. To solve this problem of race, we have another version of dynamic sequential circuits, which is known as C2MOS register, okay, or clocked CMOS register. To avoid this clock overlap problem, what we use is, this is again master stage and this is again slave stage. So, we use a PMOS here, we use an NMOS here. PMOS is being driven by clock, NMOS is being driven by clock bar. We have another stage here where a PMOS is being driven by clock bar and an NMOS is being driven by clock. Okay. So, this circuit, if we understand the working of it, suppose clock is equal to 0, clock bar will be 1. Okay. So, this PMOS will be on, this NMOS will be on, M3 and M4 will be on. In this case, if D is equal to 1, this NMOS turns on and X discharges, or if D is equal to 0, this PMOS M2 turns on and X pulls up or charges itself to VDD. Either way, what it means is that when clock is 0, okay, when clock is 0, okay, we are trying to understand the working of this C2MOS resistor. When this is 0 and this is 1, M4 is on and M3 is on. In this case, D bar will be sampled at node X. Okay. So, capacitor, load capacitor CL1 will take the value of D bar. So, inverted input will be sampled when clock is 0. Okay. In that case, if you see here M8 this clock bar here is 1 and clock is 0. Okay. So, M8 is off, M7 is off. So, the load capacitor CL2 or the output node will hold its previous output, whatever was stored before will be stored here. Okay. Now, when clock goes opposite, when clock goes 1, clock bar will be 0, this will be 0, this will be 1. Okay. So, in this case your M4 goes off and your M3 also goes off, okay. But your M8 turns on and M7 turns on. If D bar was equal to 1, it will turn on M5, okay. Q will discharge and you will get 0. If D bar was equal to 0, M8 will turn on and Q will charge itself to VDD. Either way you are going to get complementary of D bar, which is equal to D. Okay. So, this way you see that even if clock overlaps itself 0 0 or 0 1 or 0 0 or 1 1, the input data D might get sampled here, but it will not make its way to the output. Okay. So, if suppose clocks overlap, if clock and clock bar both are equal to 0, in that case this will be on, D might go to 1. If D is equal to 0, there will be a path here, X will go to 1. So, there may be a transition from 0 to 1, right, but that transition of 0 to 1 will not make its way here because M7 is off, clock is 0. Okay. So, when clock is 0 and clock bar is 0, whenever there is a 0 0 overlap, it is possible that the inverted D might get sampled here, right, because this is on, this is off. If D is 0, this will turn on and there will be a path here. So, X will take the value of 1, there might be a transition from 0 to 1, but because M7 is off, clock is 0, that one will not make its way here. Okay. Clock bar might be 0, but then if this is 1, this will be off. So, M8 and M7 will be off. So, Q will not update itself. Same thing happens at 1 1, right. If there is a 1 1 overlap between clock and clock bar, it is possible that the output the X node makes a transition from 1 to 0, okay, but that 0 will not propagate itself here, right, because M5 will avoid that, right. So, C2MOS or clocked CMOS register solves the problem of race, which happens in dynamic sequential circuits. Okay. If you use a transmission gate approach, it solves the problem of cascading, but it introduces a new problem of race condition, and that race is countered with a C2MOS register or clocked CMOS register. Okay. Now, this does solve our problem of race condition. We do get a skew tolerant solution, even if there is a propagation delay between clock and clock bar, your output is still reliable. Okay. But even with this advantage, your C2MOS approach or clocked CMOS approach still uses 2 clocks, it still uses clock and clock bar. What if we can design a solution which uses only a single clock? Okay. For that, we first understand the working of what is a positive latch. The circuit shown on the left side on your screen is a positive latch, the circuit on the right is a negative latch. Okay. So, in negative latch, when clock is 0, this circuit, this PMOS is on. Okay. If it is 0, you will get 1 here, if it is 1, you will get a 0 here. So, in bar gets sampled again, which basically means that your input will make its way. So, on a falling edge, on a negative edge of your clock, in a negative latch, your input signal will make its way to the output. In a positive latch, when clock is 1, if input here is 1, this transistor turns on and you get a 0 here. If input is 0, this transistor turns on, you get a 1 here, which means in bar gets sampled here and another inverter. So, you get in here. So, this is a positive latch, this is a negative latch. This kind of latching mechanism if you combine these two in series, okay, that is the basis of what is known as true single phase clocked register, and that in a sense is considered as a true version of a single phase clocked register. Okay. Clocked register means it is a edge triggered register where the edge of the clock is taken into account. Okay. So, if you combine a positive latch with a negative latch in series, you get what is known as TSPCR or true single phase clocked register. Let us understand its working. The circuit shown on your screen is a single phase, true single phase positive edge triggered register. Okay. So, what we are doing? We are designing, we are trying to understand dynamic sequential CMOS circuits. Okay. And in this we have come our way to a circuit where only a single clock is being used. Okay. Even though we are using NMOS and PMOS, we are not using clock bar, we are only using clock. Okay. So, suppose when clock is 0 initially, when clock is 0, M2 is on, right. So, if D is 0, M3 will turn on and X will be equal to VDD, which is 1. If D is 1, M1 will be on, so X will discharge through ground, which means on the falling edge D bar is being sampled at node X. Okay. Here when clock is 0, Y is being charged, pre-charged. So, this inverter here is in pre-charge mode, this inverter is in evaluation mode, but it is evaluating inverted D. This is pre-charging its output to VDD. Okay. Here now, when this goes to 1, M9 is off, okay, and clock is 0 here. So, this is not doing anything, this M8 is off, there is no path, and this M9 is off. Okay. M7 may be on because of this signal here 1 here, but there is no path to ground, there is no path to VDD. So, at this point Q is in hold state, it is holding its previous output. Okay. Now, suppose clock goes to 1, okay, it makes a transition from 0 to 1, M2 goes off, right. Now, whatever happens to the input, right, this goes to 1, M4 turns on, M6 goes off, right. Depending upon the value of D bar, if D bar is 1, there is a path here for discharging. So, Y will discharge to 1. If D bar is 0, Y will hold its state. Okay. Right. So, either way Y is going to transmit this D bar here, and this D bar, now when clock is 1, M8 turns on. If D bar was equal to 0, okay, M9 turns off, okay, and it goes up. If D bar was 1, M7 turns on and it discharges to ground. So, you will get D bar sampled here, it will produce some value here, okay, it will sample this value here, okay, and this comes to the output. Either way, what is happening is whenever positive edge is coming in this type of circuit, which is using a single clock, right, this is propagating. Now, your third inverter is in evaluation. Okay. This is holding, this is evaluating, this is also evaluating, this is evaluating, and it is producing D here. Okay. So, on the positive edge triggering, we are transmitting the input D to output Q. This is how a true single phase clocked register works. This is an example of a positive edge triggering. If you replace this PMOS with NMOS, this NMOS with PMOS, and this NMOS with PMOS, you are going to get negative edge triggering. Okay. So, just to summarize today's lecture, we have started and come towards a good stage in the design of dynamic CMOS sequential circuits, where we have seen that to reduce the requirement of area, to make improvements on area side, okay, the amount of transistors required or silicon area required, we can switch from static to the dynamic CMOS sequential circuit. You can implement using pass transistor, but there is problem of threshold voltage. You can use transmission gate, but that introduces a problem of race. You can use clocked CMOS approach, okay, that solves the problem of race, but you are still using 2 clocks. Okay. Finally, we have discussed true single phase clocked register, where a single clock is used, which is based on the principle of combining a positive latch and a negative latch in series. Okay. So, with this we end today's lecture. Okay. Thank you.